Okay, so we're recording. And let's give it maybe 2 more minutes and then we'll, yeah, people are still trickling in here.
Okay, I found my laser pointer.
Okay, maybe I'll get started. Are you ready to be introduced, Jane?
I think so.
Okay, yeah, so thank you all for coming, first of all, and I'm very happy to introduce Dr. Jane Breen. Jane is an assistant professor of applied math at Ontario Tech University. Jane is an expert in linear algebra, in spectral graph theory, and combinatorial matrix theory, and in particular, she has special expertise in Markov chains and random walks on graphs. Jane is from Wexford, Ireland, and she lived there before moving to Winnipeg to do her PhD at the University of Manitoba. Her PhD advisor is Steve Kirkland, who was president of the International Linear Algebra Society, so she has a very strong pedigree in linear algebra. After doing her PhD, she did a postdoc at Iowa State, and then after that moved to Ontario Tech University, where she is now. So yeah, I'm really happy to introduce Jane. She's going to tell us about, I forget what your talk is called, but I think it's something like Markov chains and random walks on graphs and Kemeny's constant. So she's going to tell us about all of those things. So go ahead, Jane.
Hi, thanks for the introduction, Mike. And thanks for having me here. And thank you to so many people for coming on a Thursday afternoon. So I'm gonna talk. This is mostly like a survey talk on this thing called Kemeny's constant, which is a really interesting thing. It's a parameter associated with Markov chains. There's lots of interesting things to think about regarding it, and I'll particularly focus on its role in random walks on graphs. And we'll get to that somewhere around the halfway mark of the talk. And don't be frightened by the fact that there's 7 sections here. This is just to structure myself and make sure I know where I'm going. So while we're going to make the shift to like thinking of Kemeny's constant as a graph parameter, I think to really appreciate what it is and what it does and how interesting it is, it's kind of fun to introduce it from the context of Markov chain theory. So I'm going to start by telling you about Markov chains as simply as I can. So the kinds of Markov chains that I think about are finite discrete time homogeneous ones. And you can just think of these as you've got some system that can occupy one of a finite number of states. And at any given time, it's in one of those states. And then in discrete time steps, it transitions from one state to another. And for any pair of states, you know, I and j, there's some transition probability that tells you how likely you are to make that particular transition. So if I'm currently in state 2, there's some probability that I go to state 1 in the next time step. And once I kind of have, the way I've kind of defined this here, it should be clear that this random process is memoryless. So what happens next depends only on the current state of the system. So once I'm in state 2, you know, I have some list of probabilities that tells me where I'm likely to go to next. And then that kind of gives me all the information that I need to know for how the system evolves over time.
Hey, Jane, sorry, can I interrupt you here? I'm not seeing your slides right now. Is that a problem?
Oh, you're not? Oh my goodness. You could have interrupted sooner. Can you see them now?
It might be, is it my fault? Did I close something that I wasn't supposed to?
I don't know. It's telling
I
me.
was seeing them. I could see floods.
I see him.
I was seeing them.
Okay, my bad. Keep going, Jane.
Okay, so should I go full screen again? I'll go full screen again. So other people were able to see them? Oh, perfect. Okay. I don't have to start again then. So let's see where we were. Right. So once you have your transition probabilities, you can collect them together into a matrix, and then it's the powers of this matrix that give you the evolution of your process over time. So you've got this row stochastic matrix. So T times this all ones vector is equal to the all ones vector. Since each row kind of represents a probability distribution of where you are next. And so, yeah, so if you want to know what happens, k time steps into the future, you just take this matrix to the power of k, and then the ijth entry there will tell you the probability of being there, getting to state j, given that you started in state I, k time steps. Right. Okay, so if I should stop, is there any questions at this point, or will we keep going? I tend to talk very fast, and so having questions is not unusual. Okay, so say I wanted to know like the long-term behavior of my Markov chain. This is something that I can calculate from my transition matrix. So it turns out that the left eigenvector that corresponds to your eigenvalue 1. So we always have an eigenvalue of 1 because my matrix is row stochastic. So if you look at this closely, you can see this is actually an eigenequation. There's just like a missing lambda equals 1 sitting in front of that vector there. So we have an eigenvalue equal to 1, and the left eigenvector, so the row vector corresponding to that eigenvalue, is a probability distribution. Or if you normalize it so that it's a probability distribution, this is called the stationary vector of the Markov chain. And what happens is, as you take powers of your transition matrix, so you see how the process evolves, it converges to this stationary vector, independently of what your initial distribution was, or which state you started in. Now that's for special kinds of Markov chains, but they're the ones we're going to think about, so it doesn't really matter too much. So what this means is that if you take this eigenvector, the ith entry of that vector gives you the long-term probability that your system is in state I. So once you have this stationary vector, you kind of have this long-term distribution of which states are most important in your Markov chain. So to give an example, when you've got this transition matrix here, where I've just picked these numbers, however, this is what your left eigenvector looks like once you've normalized it so that it's a probability distribution. And you can see here that it's far more likely in the long run that I'm going to be in state 4 than in any of the other states. And if you look more closely at the transition probabilities here, this is not really surprising, right? So if I'm in state 4, then what happens next is determined by this fourth row of my matrix. And you can see that it's with probability 0.75, I stay in state 4 in the next time step. And then there's probability of 0.25 that I go to state 3. But then when I'm in state 3, then I'm looking at this for what happens next. And you can see it's quite likely I get sucked back into state 4 again. So it's not surprising now once you look closely at our probabilities that state 4 is far more prevalent in the long run in my random process here. Okay, so that's our long-term behavior. If I wanted to consider the short-term behavior, one way to quantify this is using mean first passage times. So for my mean first passage times, I want to calculate the expected time it takes me to get to state J, given that I start in state I. So I'm kind of evolving using these probabilities, and then I want to calculate the expected time it takes me. So this is denoted Mij. And we're not going to work with this too much in this talk. So this can also be calculated using the transition matrix of my Markov chain. I've just put the formula up here because I want you to know that you can, like, once you have your transition matrix T, everything you might want to know can be calculated from T. But you don't need to worry terribly much about what this expression is or how it's derived. Just that I can calculate these mean first passage times Okay, and so going back to our example, I mean, your mean first passage times give you much more wide-ranging kind of information. So, for example, the mean first passage time from state 1 to state 2 is equal to 1, because if I'm in state 1, then with probability 1, I go to state 2 next, right? So the expected time it takes me to get there is 1 times that. But if I'm in state 2, the expected time it takes me to get to state 1 is 20 times this. So that's using this formula or this expression that I had to calculate it. And you can see from the probabilities, yeah, sure, if I'm in state 2, maybe I get back to state 1, in 1 time step, or maybe I spend a bunch of time in states 2, 3, 4 before I ever get back. So these kind of give you some information about like how easy it is to get around in your Markov chain. Okay, and so I'll start, seeing as my official job title is an applied mathematician. I'm going to talk about applications quite a bit here. I don't really know if I am an applied mathematician because a lot of the work I do doesn't involve the applications, but I really like thinking about the applications when I'm coming up with new questions to ask and problems to work on. So one of my favorite motivations for thinking about a Markov chain model is that it can be used to model a road network where, so the states here would be roads in your network, and then you have transition probabilities based on data. So you stick a traffic camera on an intersection and then you count the number of vehicles that turn left or go straight or turn right. And so this gives you some kind of approximation of what the true transition probabilities are. And then from there, you're kind of modeling, when you model this as a Markov chain, you're modeling the behavior of like a random vehicle. So obviously, like nobody gets in their car and just drives, chooses at each road at random which way they're going to go. But it does give you a sense of how well connected your road network is. The stationary vector in this situation may give you an idea of, okay, so the ith entry of my stationary vector is supposed to give me the states I'm in most frequently in the long run, or I spend the largest proportion of time in. So here, if I calculate the stationary vector, it gives me the road segments which I'm going to spend the most time on. So possibly the ones with the most traffic. And then the mean first passage times gives me a sense of how hard it is to get from A to B, or how well connected they are, or how often vehicles drive from here to there, and how long it takes. So that's one motivation. And then the other motivation, which we'll talk about a little bit more in this talk, is that you can think of all of this stuff as a way to think about graphs. So if you just think about a simple undirected graph where you have vertices and edges, the states of your Markov chain here would be the vertices. And then if you're on vertex 2, you just choose one of your neighbors to move to next uniformly at random. So I would choose either 1, 4, or 3 with probability 1/3. And then you kind of look at this as a Markov chain and determine from that, some properties of the graph. So the probability transition matrix for this Markov chain, so the random walk on a graph, you just take your adjacency matrix, which is the matrix of zeros and ones that represents your graph. So the ij entry is 1 if there's an edge between vertex I and vertex j, and 0 otherwise. And then this D inverse here is just like the degrees of your vertex, of your vertices. So you kind of divide off by how many neighbors each vertex has. See if I'm in on vertex 2, then here are my probabilities of where I go next. If I'm on vertex 3, I have 2 choices, so it's probability a half each way. And then just to note as well that the stationary vector for a random walk on a graph, the entries of that are exactly proportional to the degrees of your vertex. So the kind of most popular states in my Markov chain here are the ones with the highest degrees, the most, which is not that surprising, but it may be relevant later when we're thinking about Kemeny's constant for a random walk on graph. So I'm going to pause for just a second and see if there are any questions before carrying on.
I have a question about these probability means that you considered I not equal to J.
Say that again, sorry?
Yeah, don't you have to consider MII?
Oh, yes. So I'm going to take the convention that MII, so that this would be the mean first return time to state I. So I've only defined here mean first passage times when I is not equal to j.
Mhm.
You can also consider the mean first return time, MII, and that's actually given by 1 over the ith entry of your stationary vector. So if your state that you're thinking of is like a good one in the long run, or you spend a high proportion of time there, that corresponds to a smaller first return time.
Thank you.
Okay. Thanks for your question. That's a good one, and it may be relevant later. Okay, so it's time to talk about Kemeny's constant. So let's suppose I have a Markov chain, and I've got my transition matrix, and I've got my stationary vector W, and I've got my mean first passage times Mij. Yeah, and I've got n states here. So what I do is I fix a particular state I, and then I think about this kind of weighted average of mean first passage time. So I think of all the other states I could get to, and then I take a weighted average of my mean first passage times from my state to all those other states, where the weights are chosen, relative to how important those states are in the chain. So relative to the weight of Mij is Wj, the jth entry of the stationary vector. Okay, so you can kind of think of this, you can interpret it as the expected time it takes to reach a randomly chosen state j, beginning in state I, your fixed state. So this randomly chosen is hiding the fact that I'm choosing based on the stationary vector. But essentially, this is the expected time it takes to reach a randomly chosen state j. Now, where Kemeny's constant gets its name is that this value is a constant and doesn't depend on what you choose as your starting state. So no matter what your starting state I is, once you form this weighted average, you get exactly the same quantity. So that's why we call it Kemeny's constant. And rather than having this dependence on I, we just call it K of T because it only depends on what your transition for your Markov chain is. And you can also kind of rearrange things here a little bit and write it as a weighted average over all the mean first passage times. So this just comes from the fact that, your stationary vector is sums to 1. It's essentially just a manipulation of this expression here. And this gives you a nice interpretation, an even nicer interpretation, as now what we're doing is we're taking a weighted average of all mean first passage times between distinct states, where I'm weighting both my choice of the initial state and my destination state according to the stationary distribution. So now this gives me an interpretation of Kemeny's constant in terms of the expected length of a random trip in the Markov chain. So a random trip with both start and end chosen. Okay. So let me give you a brief history because this part is fun as well. So the very first mention of anything related to Kemeny's constant was in this kind of well-known textbook on finite Markov chains written by Kemeny and Snell in 1960. And before I show you, how it came up first, I want to note that a lot of the work that they do in that book involves this thing called the fundamental matrix of a Markov chain. So this, a lot of the things you might want to calculate about the behavior of a Markov chain kind of depend on considering the identity matrix minus the transition matrix. But that's not an invertible matrix, and so you look at this generalized inverse of I minus t. So it's just calculated as this inverse of I minus t plus, this is the all ones vector, and this is my station vector. So this whole guy here is a rank 1. And I'm going to say this vaguely, that many things can be calculated using Z. So essentially anything that you might want to calculate about the behavior of the Markov chain can be calculated from this fundamental matrix. Sorry, I should say Z and not Z, seeing as I'm south of the border for today. So for example, if I wanted the whole matrix of mean first passage times, I can calculate this from Z like so. So just to give an example of how fundamental this fundamental matrix is, this is one way it's used. Okay, so with that preface, here is the first place that there was a mention of this kind of underlying constant for each Markov chain. So here, this is a corollary to some other results where they let C be the trace of this fundamental matrix, C. And then let me translate what this result says for you. So M sub j is the expected value of something based on starting in state j. Here, this M sub pi is an initial distribution, some initial probability distribution. So this is the expected value of something based on that initial distribution. And then this y hat with an n in parentheses, this is the number of visits. This is a vector with the number of visits to your states after n steps of your Markov chain. Okay, so this overall, this y hat n j business. That's the number of visits to state j after n steps. And overall, this thing is the expected number of visits to state j, given that you start in state j after n steps. Okay, so let me just tell you the interpretation of this result rather than going any further with the detail. Okay, the interpretation of this hand wavy is that the number of times a state is visited is the same in the long run, independent of the initial state. So this converges to this constant value, independent of what your initial state, your initial distribution. That's essentially how that was interpreted. Okay, so that's corollary 4.3.6 in this textbook. And then going on a little bit further, there's a theorem 4.4.10 that says, let C be the trace of this fundamental matrix again. So some of the diagonal entries. And then let me translate this notation for you. This capital M, this is the same as ours. This is the matrix of mean first passage time. Alpha transpose, that's that's the stationary vector written in a column. C is our trace of Z here, and then that, I forget which Greek letter that is. That's the all ones vector that represents. Okay, so what this is saying here, let me see the statement translated, says that M times W is some constant value times the all ones vector, right? So this is a whole vector of things, but each entry is essentially this original way that we define Kemeny's constant. So this theorem is saying that, you know, this expected length of a random trip starting at state I is constant for all I. So this is a theorem that's in this textbook. And then the whole chapter just ends. There is no commentary. There's no, hey, isn't this weird? Don't you think this is odd? The proof even is not, you know, it's just essentially using an expression for the mean first passage matrix and then multiplying out, and it turns out that this is what you get. You know, there's no, it's fascinating. It's just written there, presented, and then the end. So it didn't actually get introduced as Kemeny's constant or as this kind of interesting measure of a Markov chain until a little bit later. So there's a textbook by Grinstead and Snell on Introduction to Probability. And the 1975 version of this book, on the very last page, there's an exercise. It's the very last exercise of the very last chapter, the very last page of the book, and it says, show that for an ergodic Markov chain, you know, this thing is constant, and we'll call it K. And then they say, the second expression above shows that the number K is independent of I. The number K is called Kemeny's constant. This is the first reference to it being called Kemeny's constant. And then the book finishes on this note. A prize is offered to the first person to give an intuitively plausible reason for the above sum to be independent of I. So like I said, the proof itself is quite straightforward mathematically, but there's not a comfortable intuitive reason for that quantity as it's interpreted to be independent of I. Now, this is how it looks in the 1975 version. In the 1997 version and any subsequent versions, this exercise has been updated to say, see also exercise 24. And then exercise 24 says, so-and-so, Peter Doyle has suggested the following explanation for why Kemeny's constant is constant. And so there's this whole description, should Peter have been given the prize? So this was I'm not going to talk really through the explanation. It uses the maximum principle. And again, like it's mathematically correct. The question is whether or not it satisfies your surprise that this quantity should be counted. And that's quite a subjective thing, I think. I do believe that Peter was given the prize. I think it was a cash prize of $50. But I spoke to Jeff Hunter. He's very interested in this side of things. So he wrote a survey paper on Kemeny's constant. And apparently the cash prize got lost in the mail. So possibly it's still up for grabs. I'm not sure. Okay. All right. So that's kind of the history of like how it was introduced and how it became kind of, known as Kemeny's constant. But I don't think people were really looking at it very much until a bit later. So there's a paper by two computer scientists in 2002, Levine and Loiseau. I don't think I'm saying that right. And so what they showed, they were thinking about Kemeny's constant in the context of the Google PageRank algorithm and considering a random surfer who's clicking on links and just the time it takes for him to find his way. So they kind of framed Kemeny's constant in that setting, and just by virtue of it being like a new thing that's introduced in this context, it got a lot of attention. And in addition to that, so we already know that it's the trace of this fundamental matrix of the Markov chain, but they also showed that if you have the transition matrix of your Markov chain with eigenvalues, so there's always the eigenvalue 1, and then there's a bunch of other eigenvalues that are strictly less than or equal to 1 in modulus. Then Kemeny's constant is this sum of 1 over 1 minus lambda j, where j goes to the n. And so once you've kind of expressed something in terms of eigenvalues, it's a spectral property of things, and it's very nice to work with. So from there, things kind of took off. So for example, they were able to think about things like lower bounds on Kemeny's constant. So you can show that Kemeny's constant, the absolute smallest it can be is n minus 1 over 2 for a Markov chain n states. And I think I might skip the proof here. If there are any undergraduates out there and you decide you don't want to listen to me anymore, you might work through the proof of this. Essentially, you just go on the fact that all the eigenvalues have to be less than or equal to 1 in complex modulus. But you do have to deal with the fact that, okay, it's fine if lambda j is real, then you have like that part of your sum is going to be greater than or equal to half. And then you just kind of have to deal with some of the issues with it being, like maybe you have complex eigenvalues, and you have to look at them in conjugate pairs. And then overall, it's easy to see from there that it's greater than or equal to n minus 1 over 2. Okay, so I guess I did just prove it, but I'll skip over this. And so you might be asking yourself, well, what transition matrix would have the smallest value of Kemeny's constant? Or what would the Markov chain look like? And it's actually just, you can think of it as a random walk on a directed cycle. Or the transition matrix looks like this. And this is kind of funny because it's not really a random process, right? It's deterministic. Once you're in state 1, with probability 1, you go to state 2, and you're just following around here. So there's no randomness involved here. And so it's not surprising then that the expected length of a random trip in your chain is as small as it could possibly be. Okay, so I'll pause there again and see if there's any questions.
Is that the only example, though? Can you have an example?
Yes, this is the unique, the only example. Yeah. Okay. Oh, this is well, it's all my favorite part, but this is my current favorite part. Applications of Kemeny's constant. So we talked already about road networks, and in that context, you can think about Kemeny's constant as like a global measure of how well connected your road network is, where you're taking into account the actual flow of traffic, and not just kind of the network itself as a graph. And so there are some co-authors of mine who worked on a project where they were modeling a road network using a Markov chain. And one of the ways in which they used Kemeny's constant was to say, okay, well, let's say I had to remove an edge, a transition from my Markov chain. So essentially I have to close a road or something like that, and then redistribute the probability somehow. Which road is the most important one in my road network? Can I determine, like, if I remove this, how much is Kemeny's constant going to change? So high values of Kemeny's constant means it takes a long time to get around. Low values means it's kind of relatively quick. And so if you can take out one road or close one road and then Kemeny's constant jumps up a lot, then that road was kind of significant to how well connected your road network was. And then there was another place it was used in globalization of the economy. Now, the Markov chain model of the economy is something that I'm not that familiar with. Essentially, it was just kind of taking different markets and like you have transition probabilities based on how they contribute to one another, like how if this one does well and this one does well, and so on. And the authors of a paper in this kind of thing used Kemeny's constant, like that. They showed that Kemeny's constant for each year of data was going down over time. So overall, the economy was becoming more globalized. That everybody was all the different markets in the economy in different continents and everything were more well connected as time went on. Looking at years of data. And then the next application I'll talk about is robotic surveillance, just because it sounds so cool. You know? So this is now my second favorite application because it's just gotten trumped by another one, which I'll tell you about. But my second favorite application of Kemeny's constant is this thing called robotic surveillance. So the idea of this is you suppose you have some persistent intruder in a fixed location of your environment, and you model your environment using a graph. So you just divide your environment up into regions that can be surveilled somehow in one time step. And then you just draw edges between vertices of this if your robotic surveiller can move then to the next region and look there. Okay, so that's representing the environment by a graph somehow. And then what you do is you think about a random walk on a weighted graph, and you want to consider Kemeny's constant for this as the measure of the expected length of time to capture the intruder. So that the time it takes my robotic surveiller to capture the intruder somehow. And so the question they asked was, well, if you just hand me the graph, can I figure out what weights I should assign to the edges of the graph so that my robotic agent can traverse the graph as quickly as possible? So how should the weights of the edges of the graph be chosen so that it minimizes Kemeny's constant? And so this seems to be quite, an important problem in robotic surveillance. And it turns out that they have this, semi-definite program that allows them to produce these weights in, I'm just going to say a reasonable amount of time because I can't remember the complexity right now. That gives them a minimal value for Kemeny's constant. And this using this algorithm then to traverse the environment and capture the intruder, it actually outperformed the state of the art by a significant amount, which is really interesting. And then my current favorite application of Kemeny's constant is in the context of disease spread, which of course we're all thinking about these days. And so there's this group of researchers that considered, let's suppose you have a contact network for how individuals might spread a communicable disease to other people in the community. So this could be something that's generated by, I know there's these apps for your phone that kind of generate a contact network based on Bluetooth codes and things like that. But let's just suppose we have the network in our hands of whether or not people were in contact for longer than 15 minutes, that kind of thing. So when you compute Kemeny's constant for a random walk on this graph, what that gives you is, how well connected this graph is in general. So if the graph is not very well connected, then that's good news because it means, in some sense, the disease isn't going to spread very well. If it is very well connected, then it might be easier for the disease to spread. And obviously, this depends on your model for your disease, but it's a reasonable interpretation of Kemeny's constant in this context. And so the idea was, well, rather than just saying, okay, well, this tells me whether or not my graph is good or not good, why don't we, for each individual in my graph, imagine if they weren't there, how much would Kemeny's constant change if they weren't there? And if Kemeny's constant increases by a lot, then removing them from the network somehow made the network much less connected. And so that individual is somehow important to how well connected the graph is. And therefore we should be mindful of whether or not they catch the disease. And in particular, perhaps that individual is somebody who ought to be vaccinated earlier or should be tested for the disease more frequently, that kind of thing. So yes, we're after a ranking of the vertices that cause the biggest increase in Kemeny's constant after removal. And just to give you a sense of how well this performs, it performs particularly well in the kind of like networks with a lot of community structures. So you can see here the highlighted nodes are the people with the most contacts, but that's not really as useful as looking at the ranking based on Kemeny's constant. You can see that this kind of perfectly lists the people who are connectors between communities. So this is a really interesting area, and there's lots of good questions to ask now because there's no good formula for, well, if you remove a vertex from the graph, can you then produce the eigenvalues of the transition matrix and then compare? There's no good expressions for that. And it's quite a tricky problem to work on. And there's no good way to kind of determine in advance like which vertices are important and which ones aren't. Very interesting area. Okay, so I'm going to pause again and see if there's any questions about that.
I hate to keep asking questions.
That's okay.
I don't seem to have an intuition as to how the weighting is assigned.
So for these graphs, let's just assume it's a random walk on the graph. So it's not a weighted graph at all, and it's just you take a random walk on the graph. But when you think about weighted graphs, it's kind of not clear from looking at a picture of the graph what weighting would be, what would be the best. So are you asking about the robotic surveillance result?
Yeah, well, I'm thinking that if it's totally random, then everything boils down to the degree of a vertex, more so than anything else.
Well, not quite, because you get these kind of bottlenecks. Well, so these ones here, like the individuals with the highest degree are the ones highlighted over here, but they're not the ones that are like most important to how well connected the overall network are. Like you can have, you can have like a very dense community here, but if it's not well connected to the rest of it, then the key individuals in terms of the random walk through the graph are these kind of bottleneck guys here. That makes sense.
Thank you.
Okay. So I think we will maybe skip section 6 at this point because I got too excited about the applications. But that's okay. And what I'm going to do is talk about some work that I did with some undergraduates while I was at Iowa State. So we've talked about Markov chains and the transition matrix for a Markov chain. But once you kind of are thinking about a random walk on a graph, you're kind of fully in the realm of spectral graph theory then, where you kind of just you come up with some matrix that represents your graph, and then you look at its eigenvalues and you kind of determine what you can figure out based on those eigenvalues. And so if you have a graph, then maybe rather than looking at the transition matrix of a random walk, a more common one to look at in this context is the normalized Laplacian of the matrix. Now, it looks kind of frightening because of these square roots, and it's kind of unpleasant for that reason to look at. But it's essentially just you have the degree matrix minus the adjacency matrix, and then you normalize with respect to the degrees. And so the reason that this comes up in the context of random walks on graphs, oh, sorry, here's an example. So you can see the square roots and, you know, oh dear. But it gives you a sense of like, you know, where the edges are and what the degrees of the vertices are and that kind of thing. And the reason this comes up in the context of Markov chains is that it is not too hard to show that your normalized Laplacian matrix is similar to something that looks like your transition matrix for the random walk, except it's subtracted from the identity matrix. So what that means is if you look at the eigenvalues of your normalized Laplacian, well, they're always going to be between 0 and 2. And then they're in one-to-one correspondence with the 1 minus lambdas of your transition matrix, right? So Kemeny's constant for your graph then is just the sum of the reciprocals of the non-zero eigenvalues of your normalized Laplacian. Okay, so with that kind of defined, we're going to just work with the normalized Laplacian from here. And of course, you know, the kinds of things I might want to ask when I'm working on a problem like this is, well, what's the biggest and the smallest that Kemeny's constant can be, just for a random walk on a graph? And it shouldn't come as any surprise that the minimum value of Kemeny's constant for a random walk on an undirected graph, that happens when you've got the complete graph. So Kemeny's constant for a complete graph on n vertices, so where everybody is connected to everybody else, this is n minus 1 squared over n. And then would anybody like to take a guess as to what kinds of graphs you would get a maximum value of Kemeny's constant for?
Maybe just a line.
Oh, you've fallen into my trap. So yes, you're inclined to think that, you know, if you've got large distances in your graph, that's the thing that causes Kemeny's constant to be large, because you've got, you know, this expected length of a random trip in your graph. But actually, it looks something more like this. And this kind of gets across one of the things about Kemeny's constant that we tend to forget, and that I think is key to answering this question of, you know, an intuitive explanation for why Kemeny's constant is the way it is that it's a weighted average of the mean first passage time, and the weights are determined by how important your states are in your chain. So when it comes to random walks on graphs, it kind of weights trips between high degree vertices more prominently than other trips. And so you do get, you know, large values of Kemeny's constant for a path. So if you took a path, this is what, 18 vertices, I think? Maybe a little fewer. If you arranged all of those in a path, yeah, that wouldn't have a good value of Kemeny's constant, but you actually get worse if you make two big cliques like this and then join them with a slightly shorter path. And so this is not actually proven that this is the maximum value of Kemeny's constant, but it is on the order of the largest. And I have, there's kind of, this hasn't really been considered, but the graph with the maximum value for a mean first passage time is something kind of not that far off, except we only care about one of the mean first passage times being bad here, rather than kind of some weighted average of it. And so Kemeny's constant for this graph is on the order of n cubed, and that's the largest order that Kemeny's constant can be. And so your colleague here has proven back in 2018 that if you just looked at the smallest eigenvalue of the normalized Laplacian, this 1 over that is known as the relaxation time. The maximum relaxation time is on the order of 1 over 54 n cubed. And then a bunch of us came along in 2019 and specifically looked at Kemeny's constant here and showed that that it was equal to 1 over 54 n cubed plus a bunch of lower order terms. And I'm just keeping an eye on the time here. I'll talk very briefly about like the techniques that we use to show this, just to give a sense of, you know, what working with Kemeny's constant is like. Now, I don't want to frighten anyone off either, so I'll try and keep it, you know, I'll try and convey the interestingness and the niceness of it. So this was work that we did with a group of undergraduates here down in Iowa State, and a graduate student, Kate, and Steve Butler, who is my postdoc mentor. So we did this over a semester, and essentially the idea was we kind of wanted to look at this graph and try and show that it was the worst possible for Kemeny's constant. What we ended up doing was developing a bunch of kind of spectral techniques for working with the normalized Laplacian and writing down the eigenvalues of a graph that has lots of nice symmetry. And so the idea was, if you have a graph like this, well, it looks like, you know, there's a lot of symmetry over here and over here. And wouldn't it be nice if we could just kind of ignore what that part is and just look at a simpler version of the graph? And maybe we add a loop to kind of represent that something was going on here with our original. But is there some way that in calculating the eigenvalues of a graph, I can reduce it somehow to a nice situation? And so the technique that's developed around here was essentially like, when you want to come up with eigenvalues for a graph, let's just think about the adjacency matrix for a graph for a second. Once you find an eigenvector that works, then you've got your eigenvalue. So you just have to satisfy an eigenequation somehow. And you can think about an eigenvector as like a weighting of the vertices of your graph. And as long as you pick the weights of your vertices in such a way that there's this kind of nice local behavior where if you're standing on one vertex and looking at all your neighbors, that they kind of add up to the right thing, then you've got an eigenvector and you're great. So this looks really nice for the adjacency matrix, because you look at an adjacency eigenequation, you have a times x equals lambda x. And if you look at the entry corresponding to a particular vertex there, what you've got is, you know, on the left-hand side, you have the sum of eigenvector entries of vertices adjacent to your vertex v, and then that should equal to lambda times the eigenvector entry of v. So that's what this looks like here. So you have this nice local condition where you just look at, you sit on your vertex v and you kind of look at your neighbors and they should add up to something times yourself. So if you can pick this weighting well, then you're good. And so like when you've got a lot of symmetry, it's not too hard to be able to pick these weightings in an appropriate way. So you kind of like get a bunch of eigenvalues for free from this symmetry, and then you're just left with something simpler to work with. Now, we wanted to work with the normalized Laplacian, which is not nearly as pleasant. And so I'm going to just skim over this because I see I have 2 minutes left. So essentially, you just kind of have to rearrange and do the best you can. So you can kind of rearrange some stuff so that you have like 1 minus mu times x. But then like that nice local behavior comes from the adjacency matrix. So you kind of want to get that on its own. And the best you can do is like the adjacency matrix times this e to the negative 1/2 x. And then you kind of manipulate what's over here to get something similar, so that your local condition ends up looking like, okay, if you're standing on vertex b and you've got your entry, then there's this weird condition with a degree and with 1 minus mu, and then that looks like the sum of your neighbors. And so that was what allowed us to produce a result that let us do this nice thing when we collapse. You just have to kind of take the weight into account there of these collapsed groups. And you can do this further, so you have these identical subgraphs that you can say, wouldn't it be nice if this just looked like, you know, a single path where I account for the weight somehow, and then I can collapse my case, and again, I'm in a nice situation. So this is what the result looks like. I'll not dwell on this for any length of time at all. Essentially, you have these kind of subgraphs that are twins, and then you form a new graph, and then you can get your eigenvalues, and they have a certain multiplicity, and then you can do this other thing, and it's gone off the page, but you get some other eigenvalues from there. And so I don't want to, it's actually quite nice. It's just hard to write down. But this is what allowed us to show that Kemeny's constant for this graph was this value. And we kind of did it for some other examples as well, where you have different numbers and we're still pretty convinced that this is the worst case. And that's something that Mike and I have considered working on for a little bit as well. So I'm going to skip now to some possible future problems to solve because it's not letting me. There we go. So there's lots of things to think about, and it's because it's such a nice kind of intuitive thought. There's a nice way to think about it in terms of, you know, this expected length of a random trip. There's lots of things to ask for. So you can think about it for like different graph families. Trees are done, complete multi-partite graphs are done, regular graphs where every vertex has the same degree. That could be really interesting because you see that the worst case we have is when there's like these really high degree bits and then these really low degree bits. So if you can understand what's going on in the regular case, maybe it gives you more of a sense of what's actually going on. And you can kind of go further in the class of regular graphs, distance regular, strongly regular. And then there's relationships with other graph parameters. So how does distance play a role in this situation? So what's the possible range of Kemeny's constant where you fix the diameter of the graph at the maximum distance and two vertices are apart? What if you fix the maximum degree so that you can't have peaks that are like too big that are causing these bottlenecks? And then how is it related to other measures of connectivity? So yeah, lots of really interesting things to think about. Other measures of clustering as well. But I'm gonna stop there so that we have time for questions. And thank you very much for your time. I really appreciate it.
Okay, thank you, Jane. Do we have any questions for Dr. Breen?
Can I ask a question? This is Jiang Tao. Yeah, so I really like the talk and also the example with connection to COVID-19. So I observed there are several lower bound and upper bound. So I think in the real application, it is possible that some information from the graph is missing. So you only have a partial graph, and also maybe the graph follows certain model like others, maybe some random models. I just wonder if if graph is incomplete or it is actually a random graph. Is there some result about the Kemeny constant, like the distribution or the lower and upper bound, like the result, if the graph is really like that way? Yeah, thank you.
In the random graph case, I'm sure there's something at least related to the normalized Laplacian eigenvalues. I'm sure there's bounds on it based on like you have an Ehrlich-Renier random graph. I think Kemeny's constant has been considered for those. For an incomplete graph, though, that's a very interesting question. And yeah, with Kemeny's constant, it's so dependent on, you know, like what the whole thing looks like, and it's hard to know if there's maybe certain cases where you could come up with bounds on it. I think it's a very interesting question to ask, like you said, particularly in the case of this COVID-19 modeling, that if you know that your contact network falls under a certain class of graphs, that you could say something. So that's certainly something that's worth studying for that reason alone. I'm not sure how much headway you could make on the partial graph thing, but it's worth looking into for sure.
Yeah, thank you very much.
Yeah, thanks for the question.
Okay, Tim, do you want to ask a question? I see your hand up.
Sure. So thank you, Jane. That was a great talk. I really enjoyed it.
I just want to say a bit of history that since I've been organizing and coming to Colloquia for a very long time at Villanova, you mentioned Grinstead in his book. So he was at Swarthmore, and we've had him for Colloquia on I think at least 2 occasions over the past 20, 25, 30 years or something like that. Anyway, so that was really nice.
I've actually spoken to anybody like from that side of thing. You know, I came at Kemeny's constant from a linear algebra perspective, and I've never actually gotten in touch with anybody who's who's one? I'd love to get their take on, whether they feel the intuitive question has been answered or not.
Yeah. So I just have a quick question, which is, I'm not a graph theorist. I know a very small corner of a little teeny bit of spectral graph theory. So is there one of the usual ideas about finding the clicks in a graph is that Fiedler vector idea of using since the Laplacian is positive semi-definite, then you can use the smallest non-zero eigenvalue and its eigenvector to help you find those clusters. Is there any connection to that and that barbell graph thing you were drawing at the end?
I don't remember what it. Yeah. So oh yeah, the barbell graph. Yes. So what my understanding of the Fiedler vector, school of thought when it comes to clustering is that there's no distance taken into account. And so it does tell you about where the clusters are in the graph. But it doesn't care if you put a big distance between them, the two clusters or not, whereas Kemeny's constant does. So like graphs with the worst, sorry, I shouldn't say the worst, graphs with the largest values, I guess it's smallest values for the algebraic connectivity. The distance between the two clusters or the many clusters doesn't come into play at all. But that's one thing that, in the COVID-19 application that we're thinking about. So how is Kemeny's constant related to other measures of clustering? If you compare how vertices rank under different kind of, I forget the word, under different ranking systems, you can kind of see in certain examples, what features of the graph, cause this to happen and cause that to happen. There is some distinction between what Kemeny's constant does with things versus the Laplacian and the eigenvalues of the combinatorial Laplacian. And I think it's mostly because of this distance thing that it doesn't take into account how far apart or how long it takes you to get between two vertices.
Yeah, thank you. That makes sense, because in that COVID example, the Kemeny's constant's helping you to find the ones that sort of are the bridges between the different communities. Yeah. Okay. Thank you very much. It was a great talk.
I see Ryan has his hand up. Do you want to go ahead?
Yeah, that was really interesting. Thank you. So when you were talking about the application to maps, I was thinking, especially if you're putting together a graph that encompasses like all of the roads in the United States or something, it's going to be a very, very sparse graph, right? And maybe with today's computers, you can calculate this stuff so fast it doesn't matter. But if you have a really, really sparse matrix, could you find Kemeny's constant for a subset of that matrix and then extend it or interpret that somehow to what it would be for the entire thing so that you don't have to do the entire calculation?
Right, so I think you are either asking one of two questions, and they're both good questions, so I'm going to answer them both and assume you ask them both. So it seems like one of the things you're asking is it possible that you could kind of construct Kemeny's constant for like a bigger thing based on like smaller things that have sparse connections? And not yet, but that's a really nice question. I think it's tricky. But it's something that's worth exploring. And one thing that I didn't get to is that there is this combinatorial expression for Kemeny's constant, which is really unfortunate looking to put it together. But it depends on the number of spanning trees and spanning forests of your graph. And so if you can decompose like a big network into smaller chunks with small connections between, it might be easier to count these things. And then the other thing that I think you asked was about, how hard is it to calculate Kemeny's constant for this whole big thing? And it is actually quite tricky. So you have to calculate all the eigenvalues, which is not what is it, n cubed, or they've reduced it recently, the computational speed of computing eigenvalues for an n by n matrix. But if you're using Kemeny's constant to find like important roads in your network, rather than just a one-time, this is how well connected my network is, you're trying to do like lots of computations over and over. It's not doable, really. And so there's a need for new techniques in that department. So I don't know if I've answered your question now, if you want to rephrase it at this point.
No, I think that was good. The main part of it was like assuming a matrix that's relatively uniform, like could you interpolate Kemeny's constant for a subsection of that matrix and then extend it to the rest? And it sounds like there's not really a good answer for that. So
yeah, I think the answer is no, or maybe in certain cases if you know the structure in advance and it has some version of nice structure, but like even those kinds of results don't currently exist. I think, you know, that if you have a graph and you've joined it like this, if you have two graphs and you join them like this, here's an expression for Kemeny's constant. I've tried that, and it actually is quite tricky to come up with expressions based on like some kind of graph product operation. Yeah.
thank you.
Yeah, no worries.
Okay, so I think we're going to do one more question. Deer has his hand up.
Yes, thanks a lot for the talk. I just had one question and a follow-up question related to the dumbbell graph. So over here, we've used one random walk and the expected times associated to it. Is there, can we define a generalized Kemeny's constant using multiple random walks and then their sort of, so I expect it really speeds up the discovery of nodes if there's multiple random walks, and graphs like the dumbbell graphs can be reached faster, much faster than say the complete graph. So like ratios of different Kemeny's constants, can they tell us something about the structure?
So it sounds like what you're talking about is like possibly ways of approximating Kemeny's constant based on, you know, sample random walks, right? So Kemeny's constant, the way I understand it, because I never really have to do very much of computation. It's like if you have the random walk, this is like the behavior as you tend to infinity. This is not like a sampling thing. But yeah, you're right that if you try to approximate Kemeny's constant with something that has this kind of community structure by running a random walk and trying to measure and then put together this calculation, that it's very slow for that reason. And so I haven't considered the possibility of you know, doing multiple random walks and approximating based on that. But it sounds like kind of distributed computing, like that kind of thing you're talking about. Is that, am I understanding your question correctly? Or
I'm not sure. So I was thinking of like starting, say, k random walks from the same node, and then calculating the expected times using when the first time of contact, expected time of contact, and then getting a Kemeny constant that way.
Yeah. So I think, yeah, you're right that multiple starting points would be better than for using that as an algorithm. Something similar has been done, like statistical methods to compute. It's not Kemeny's constant, it's the backwards version of it. So rather than starting at a state and getting the expected time to reach a randomly chosen one, you pick a state and it's the expected time to arrive at yourself. And so there are, you know, statistical techniques for computing that are based on what you're describing, like kind of initiate multiple random walks at a particular node and then count based on that. Yeah.
Thank you. Thanks.
Okay, so yeah, if anybody has other questions, you can feel free to follow up with Jane. I'm sure she'll be very happy to talk to you for as long as you want about Kemeny's constant. But yeah, let's thank Jane again. Thank you, Jane. And yeah, thank you all for coming, and thanks Jane again for giving this talk.
Yeah, thanks so much for having me. I hope that sometime, you know, I can actually visit in person.
Yeah. Okay, so keep your eyes open for our next colloquium, which is I don't know when. It's yeah, it's maybe on the schedule, but I'm not sure. It's not in the near future. So keep your eyes open, and we'll send out an email. So thank you all for coming.
The next one scheduled is April 7, I believe.
Good. Okay, thank you all.
Thanks, Mike.
Yep.
Thank you.
Everybody.
You want to stop the recording, Mike?
Yes.
Thank you, Dr. Tate.
Sure. See ya.
Great talk, Jane.
Can I ask